Hi, I'm Clay Rehrman.
I'm Sam Allen.
I'm Kaveen, and this is our Lapley-Poisson's ratio presentation report. So digital image correlation is the method we're using for this lab, and it's used to identify material strain and deformation. And we're measuring Poisson's ratio, and we're going to find the magnitude of it, which will determine the material's behavior and how much the material changes. And the materials we'll be using is copper, aluminum, and polymer.
The first step is to prepare and mount a dog bone specimen within the testing machine. After that, we prepare GOM data collection software and a camera, which will be positioned to closely survey the speckled side of our dog bone sample whilst it is placed in the gauge. Then we will record data by taking the videos through the camera using the GOM Snap software. We will follow this procedure for dog bone samples of aluminum, copper, and polymer. Finally, after these videos have been taken, we will analyze each using the GOM Correlate software.
Uh, this is the data that we obtained from GOM Correlate. And on the left side is the polymer copper data. The line on the top of each graph is axial strain, and then the line on the bottom is the lateral strain for each one. Um, those graphs were very clear. You can see that the line on the top, the axial was going upwards direction, and then the transverse was going downwards. The aluminum graph is not as clear due to errors that we had during the experiment itself. But the same thing, the line on the top is the axial, and the line on the bottom is the lateral. Uh, Here are the Poisson ratios and the percent error that were calculated using that data. Um, as you can see with the copper and polymer percent error, they're relatively close together, um, meaning that whatever issues we had was most likely just due to us not applying enough force for similar things during the experiment itself, while aluminum's was much worse due to what we can only presume to be camera issues and just issues using the software itself. Uh, the group going into the lab expected to get accurate Poisson ratios from the GOM software that we were using in the lab. Um, what we actually got was only somewhat accurate, and that can be mostly assumed to be error from us, just not using the software properly, or not positioning the camera right, not doing enough force on the part at the time it was recorded, and aluminum being very off was also due to just uh, same thing, but only an additional operating error during it. And when done correctly, GOM can actually be a great software to measure the data, uh, and it is much more accurate than the methods that we use in practice.
So in the end, we got copper and polymer percent errors less than 30%, while aluminum's percent error was greater than 40. This indicated that our copper and polymer data was much more accurate than our aluminum data, again, due to the errors that Sam described before. The DIC method provided Poisson's ratio values that were within reasonable percent error of true values. So therefore, our hypothesis was largely supported that GOM correlate could be used with GOM snap to get relatively accurate values for the Poisson's ratio of materials in an experiment. In the end, DIC proved an effective tool for calculating material properties in an experimental setting. So for some future work recommendations, we would like to be more careful to use the DIC software, GOM-SNAP and GOM-Correlate, correctly, because to elaborate more on the errors with aluminum, what happened was we opened up a project and then we had camera issues, etc., and the project was just a failure in the beginning. But then we did not close that project down before we started our actual aluminum project. This caused errors in the data, which ended up actually negatively affecting our percent error. Also, we want to subject parts to more force to produce more strain. This will help give us broader data sets and thereby will give us more data to work with when we are analyzing the Poisson's ratio values.
So these are the references that we use for this experiment. And these are some questions. So why is Lumen's data so scattered and inconsistent compared to the rest of the samples? The reason for that is Sam mentioned earlier, camera issues, and we also had incorrect software usage. We opened up Gong Snap and didn't close it, and opened up Gong Correlate, and that led to the failure in aluminum. And what are some other methods to acquire Poisson's ratio? The tensile test with strain gauges to measure the longitudinal and the transverse strains during the test can also help determine the Poisson's ratio.
Thanks for watching. Bye-bye.